so we're going to introduce the logarithmic function. So very, very important, very fundamental. Yeah, so the logarithmic Okay, so let's just start off with a definition. Okay, so what is the logarithm? What does it mean? So let me just set up some notation. So let x be strictly greater than 0 and b be greater than 0 with also b is not 1. Okay, so it's kind of that same assumption as before. We want b to not be 0, be greater than 0, but not be 1. Okay, so that's the setup with the notation. All right, and here we go. So the function y equals log, in the subscript I put a b, so log base b of x is equivalent to b to the y equals x. Okay, so I will explain this, but this is the definition. Okay, this is b to the y, so b is the subscript. It's b to the y is equal to the input x. Okay, now how do we say this? Like, what's the pronunciation of this? So log base b of x is read aloud as, like, how do we speak it? Like, how does it sound? It's read aloud as one of two things. So it's going to be the logarithm of base b of x. That's one way to read it aloud. And another way, which is the way I will say it, just because it's a little quicker, or log base b of x. Okay, so I will almost always shorten the word logarithm to just log. It's just easier, and it'll just save time. So whenever I say log, it will mean logarithm, and I'm going to highlight this one because this is the one I'm going to say most often. Okay, so log base b of x just stands for this notation: log subscript b and then parentheses x. All right, so that's the language. Okay, so let's just kind of reinforce what I'm saying here. So in other words, log base b of x equals y is, or means, so it's just another way of writing like an exponent. It's like log base b of x equals y means, so you take the subscript and you raise it to the other side of the equal sign, which is y, and you set it equal to the input of the function x. Okay? All right, and just one more way, said even differently. Log base b of x is the power you need to raise, it's the power you need to raise b, it's the power you need to raise b to get x. Okay, so when you're given an expression, log base b of x, the result of this, you need to ask yourself mentally, b raised to what power will give me x? And that will be the result of log base b of x. That's what it comes out to. All right, we're going to do examples. We're going to do a lot of examples, okay? So that's kind of just like a preview. Okay, and let me just quickly talk about the domain here. So this is a function of x. The input is x, and the output is log base b of x. So let me just say a quick note about the domain. So the domain, so remember, this is a function, y equals log base b of x. you can only input positive numbers greater than 0. So it's going to be 0 to infinity with parentheses, 0 to infinity. Okay, that's the domain. And its range is going, so all the y values that it achieves, it actually hits the whole real line. Okay, so it's going to hit minus infinity to infinity. All right, so we're going to reinforce this later. This is just like just some quick properties of the function. Okay, so any questions? Okay, good. So let's, so you can see here that logarithmic form and exponential form are very, very closely related. So let's just practice converting between the two, meaning given an expression like this, log base bx of y, give me its corresponding exponential form and vice versa. So let's just jump between the two so we can get really comfortable with this logarithmic notation. All right, so here's the heading. It's just going to be converting between logarithmic and exponential form. Okay. All right, so here we go. So let's do the first example. So we'll do log base 3 of 9 equals 2. Okay, so in the expression, I have a b, a y, and an x. So let's identify what those values are in this specific equation. Okay. All right. So here, so b is always, it's the subscript of the logarithm. Okay. So b is going to be 3 here. All right. Okay, x is the input of the logarithm, that's 9. It's the input, and y is always the thing on the other side of the equal sign. It's the output, which is 2.
Could y also be defined as f of x, although I don't want to confuse it that much?
Yes, definitely.
Okay.
I just use y because if I wrote b raised to the f of x power, it just looks kind of strange. I want to think of y as a number right now and not a function, but yes.
No worries. Yeah, just wanted to see.
Yep. Okay, so here we go. So we're going to write this in its corresponding exponential form. So just recall, I'm just going to write it again. Log base b of x equals y. This leads to b to the y equals x. All right, now let's do it in our specific case. Log base 3 of 9 equals 2. Okay, so I do 3 is our b, y is 2, and our x is 9. So this is equivalent to 3 squared equals 9, which of course is true. Okay, so any questions how I went from this left side to the right side, which is exponential form? So we started with logarithmic. And we went to exponential. Okay, so when you do this on the homework, you do not need to be this explicit with writing, okay, b is this, x is that, y is that. I'm just doing it just because we're first introducing this concept. Okay, this is something new. But of course, you don't need to be this explicit. All right, so let's do some more. Let's really try and get this solidified. Okay, so here's a slightly different one. How about log base 6 of the square root of 6 equals 1/2? Okay, so this subscript here is b. This is y, and this is x. Okay, so I do b to the y equals x, and this will be 6 to the 1/2 equals the square root of 6. Okay, and that of course is true because a 1/2 power is the same as taking a square root, as we did in the first week of class. Okay. All right, so any questions? Okay, so hopefully this is okay. All right, now let's go the other way. Let me give you an exponential, and then I want you to write its corresponding logarithmic. All right, so how about this guy? 2 to the 3rd power equals 8. Okay, so what I like to do, I just like to identify our b, y, and x value. So here, so b is, I like to think b is the base. It's the base of the exponent. That's how I remember it in my head. So you go to the base of the exponent, and it's 2. So b is 2. The exponent, like the power, is 3, and x is 8. Remember, it's b to the y equals x. Okay, so let me just write that. So b to the y equals x, and this gets transformed to log base b of x equals y. Here we have 2 to the 3rd equals 8. So let's just plug in. So I have log base b is 2, so I put a 2 in the subscript. The right side of the equal sign is the input, so it will be 8. And the right side of the equation is the power, so it'll be 3. So log base 2 of 8 equals 3. Okay. So it may be a little tricky, but practice will, of course, make this perfect. All right, one last guy. 10 to the minus 4 equals 1 over 10,000. Okay, so let's just kind of jump right to it. Remember, we do log base b of x equals y, and b, so b is always going to be the base of the exponent, so it's 10, right? So it's going to be log base 10. The input of the logarithm will be the other side of the equation, so that's going to be 1 over 10,000. And then the exponent itself will be the right side of the so it will be minus 4. Okay, and you can of course check your answer by going back into exponential form and making sure you got the same thing you that was presented to you in the beginning of the question. Okay. All right. So
I have a question.
Yeah.
Is there ever an equation where like the question is incorrect, like it isn't like that number?
Oh, no. These are just made so they are correct, just to illustrate the conversion and practicing converting between the two. So no.
Thank you.
Mm-hmm. Okay, good. So this is how you convert. Now let's actually evaluate some logarithms mentally. Okay. So let's do some mental math. Evaluating. So evaluating logarithms mentally. All right, so we don't need a calculator for any of this stuff. The only thing you need a calculator for is that compound interest question on the homework. Everything else, you really shouldn't be using a calculator. Okay, so here we go. So I just have to write a little bit and then I'll explain. Okay, so given some logarithm, log base m of n, log base m of n, we can find its value by asking ourselves. So we ask ourselves, like the following question. M raised to what power is n? Okay, so I never know if the question mark goes inside the quotes or outside the quotes. Never knew that. So does anyone know when you do quotes, does a punctuation go inside or outside?
Inside.
Yeah, inside.
Inside. Okay, so this is right?
Yeah.
Okay, cool. All right, thank you. Okay, so that's the result of log base m of n. It's the power I need to raise m to get n. All right? So there is another way to think about it. So equivalently, we can set y to be equal to log base m of n and rewrite as m to the y equals n and solve for y. Okay, so what's going on with this second sentence I wrote? All I did is I just assigned a variable y to be log base m of n, and I wrote it in its exponential form, just like we did in the above examples. Okay. And then you can just kind of look at it visually and be like, okay, what does y need to be for this equal sign to hold true? And that will be the answer. Okay, so let's just jump straight into some examples, okay? So first one will be log base 4 of 64. So when you're given this expression, you ask yourself, 4 raised to what power? 4 raised to what power is 64? And that will be the result of this. 4 to the what is 64. Okay, or just for that other way that I wrote out, or you set y equal to log base 4 of 64. You convert to exponential, just like we did, 4 to the y equals 64, and you see what y is. So look, you're just rephrasing the question in like some notation. You still need to find the power you need to raise 4 to get 64. Okay, all right, and that is going to be 3. Okay, the answer is 3 because 4 to the 3rd power will actually give us that 64. Okay. So any questions? So this is very fundamental. So I just want anyone to stop me if we're having trouble right now. So the answer will be 3. All right, let's move on. Some more examples. Okay, so evaluate log base 2 of 4. Okay, so when you're given this expression, you ask yourself, 2 raised to what power is 4? Okay, that's what you need to, that's the question you need to answer. Or you do it in that log in that exponential form. So or rewrite as, remember this is the same as 2 to the y equals 4, and solve for y. Okay, so you're looking at, what value of y will make this equation true? And I think it should be kind of quick to see that here y should be 2. Okay. Okay, because 2 raised to the 2nd power is 4. Okay, so any questions? Okay, one more of these. Log base 121 of 11. So that's kind of interesting. So let me just, what is this? What question do you need to ask yourself to evaluate this? Well, you need to ask yourself, 121 raised to what power is 11? Or equivalently, 121 to the y equals 11, and solve for y. Okay, so any ideas here? How do I get, what do I need to raise 121 to get a smaller number?
It would be 2 to the half. It would be the square root.
Yes. Yes. Fractions are totally allowed. Excellent. So y is 1/2. Yes. So very good. So well, 121 to the 1/2, which is this exactly the same as the square root, that will give you 11. Excellent. So the answer is 1/2. Good. So this just kind of highlights the fact that the logarithm can evaluate to not just whole numbers, but fractions and so on. Okay. Very good. Very good. All right. So let's keep going. Yes, I have one more of these.
Quick question, kind of like, it's basically just confirming what I think, but like, if the information we don't have is the base, then we are also using not fraction, but square roots to solve, right?
So you're saying if you don't have the base,
Yes.
but you have the other side?
Yes.
Um,
Then you're also like not square rooting, but like rooting.
Let me think for a second. So you're saying if we have b to the 1/2 equals 11?
Yes.
Let's solve for b.
Yes.
Yes.
Then we have to like root it to the other side.
Yes. So by rooting it, I would say square both sides? Is that what you mean?
No, thank you. I guess that makes things clear. Thank you.
Yeah, because then
I was like transferring I was going crazy, sorry.
Okay. Yeah, because we need to get rid of the 1/2 power, so you do that, and you get b is 11 squared, which is 121.
Thank you.
Yeah, sure. But yeah, so we're not going to be solving for the base in any of these questions, I don't think. So, okay, so one more guy. So this one's also slightly different. So log base 3 of 1/9. Okay. So what's the question that we ask ourselves? 3 raised to what power? Okay, I want this to be like always in your head when you're given a logarithm. 3 raised to what power is 1/9? Or equivalently, you can think of it as 3 to the y equals 1/9.
-2.
-2, absolutely. Good. So we know that 3 to the -2 is the same as 1/3 squared by our work on negative exponents. And of course, that's 1/9. So it's this power right here that's the answer, the -2. So the answer is -2. Very good. So this is also highlighting the fact that the logarithms, they can come out to be negative numbers. They don't need to be, positive whole numbers. Okay. All right, good. So it seems like this is not that bad. Just please let me know if you're having any troubles. All right. Okay, so now we just want to talk about the common logarithm and the natural logarithm. These are just going to be specific bases of the logarithm that we just like to designate a name for. So this is really not anything new right now. I'm just giving some terminology to specific cases of b, of the base. So the first one will be the common logarithm. So this is the so-called common logarithm. Okay, and what this one is, it's when the base is 10. Okay, so we care about the specific case when the base is 10, when that b is 10. Okay, so really, I'm not saying anything too new here. We're just giving a piece of notation for log base 10. Okay, so when the subscript of the logarithm is omitted, so there's no subscript, you just have log with no subscript, and just written as log x. Okay, see how there's no subscript? I just wrote log parentheses x. This is defined to be base 10. This is defined to be log base 10 of x. All right, so it's just shorthand. It's just like a shortcut or an abbreviation for log base 10. When there's no subscript, it's understood to be base 10. So just in other words, log of x is just log base 10 of x. That's all. Good. So that's it. That's all I have to say about that. Just when you have a log x when you have a logarithm without a subscript, think of it as log base 10, because it is log base 10. All right, good. We have another one of these for a specific base. Okay, we have another one of these, and that's the natural logarithm. The natural log. Okay, so which one is this? This is going to be log base e. Okay, so do we remember Euler's number e from last class? It arose as a specific case of the compound interest formula. So we're going to end up caring a lot about log base e. All right, it's going to be very important to us, and especially later down the line in calculus 1, 2, 3, and many areas of math. Okay.
Is that the default base for natural log?
Default base. What do you mean by default?
Yeah, it's probably not like the right way to reward it, because in some calculators, when you just type in log, it just automatically comes to log base 10. So
exactly.
Yeah.
So right. So if you just see log, you want to think of it as log base 10. But as always, context is going to tell you, like it will probably tell you on the paper that you're looking at, log here means this or it means that. So let me just write formally natural logarithm. So recall the number e. So remember the number e, it was like approximately this 2.718 ... Okay, so the decimal expansion went on forever. And here's the definition. So how do we, what are the symbols for it? You actually just do ln of x. ln of x. This is defined to be log base e. ln of x is log base e of x. Okay, so again, this is just shorthand. I'm not really defining anything new. I'm just giving log base e its own specific symbol or notation for ln. Okay, so let me just write that. So thus, log x and ln of x, natural log of x, are shorthand for log base 10 of x and log base e of x, respectively. Okay? So it's just shorthand. All right. So that's really all I have to say. If you see ln of x, which is read aloud as natural log of x, just know in your head, that's log base e. Okay, that's a logarithm where the base is e and e is Euler's number. All right, good. Okay, so let's jump to finding the domain. Okay, so we do have a new function here. We want to find its domain. Okay, so finding. Okay, so finding the domain of a logarithmic function. Okay, so right, so as stated earlier, the domain is 0 to infinity. So as stated earlier, the domain of log base b of x is parentheses 0 to infinity. Okay, so we can only take the logarithm of numbers greater than 0. We only take the logarithm of numbers strictly greater than 0. Okay, so here are the steps. This is how you do it. Given a logarithmic function, how do you find its domain? Well, this is what you do. Step 1, you set the input to be greater than 0. Step 2 is to solve the inequality. Solve the inequality from step 1. And third is to write your answer in interval notation. Write in interval notation. Okay, so so this should look familiar to finding the domain of what function? Not exactly the same, but similar. Do you remember some function we had to set the input to be greater than 0 or greater than or equal to 0? What does this look similar to?
Square root.
Like, yeah, fraction and square root.
Yes, yes, good. Square root and even roots, 4th roots, 6th roots, and so on. It was those, so actually cube roots and odd roots you don't need to set to be greater than 0. We never discussed that, and don't worry about it, but it's those even roots. But yeah, square roots in particular. Good. So it's actually very similar, except greater than or equal to 0, it's now strictly greater than 0, because you can't take the logarithm of 0. That's it. All right, so let's just go straight to examples. I don't think this is going to be that bad. Find domain of log base 2 of x plus 3. Sorry, I just want to write this a little neater. Find the domain of log base 2 of x plus 3. Okay. Now, in these steps, the base of the logarithm is not mentioned at all. And that's because it doesn't matter. Okay, so when you're doing these questions, finding the domain, you don't need to even consider the base. It doesn't change anything. All right, so don't worry about, so the fact that there's a 2 in the subscript doesn't change anything right now. Okay, so all you need to do, so the input here is what? It's x plus 3. So you set that to be greater than 0. So you solve x plus 3 strictly greater than 0. Okay, this is not greater than or equal. It's a strict inequality. Good. And this is just x is greater than minus 3. So you subtract 3 from both sides. And now we just go into interval notation. And that will be parentheses -3 to infinity parentheses. Okay. So this is nice now. Our previous work of solving inequalities and putting our answers in interval notation is really coming in handy. All right. So there is a reason why we do things in a certain order. Okay, so any questions? All I did is I took the input of the logarithm, x plus 3, set that to be strictly greater than 0, solve that inequality, put it in interval notation. So that's that. Okay, next example. Okay, this will be similar. Domain of log of 5 minus 2x. Okay, all you need to do is identify the input and set it to be greater than 0. So this is really all you have to do is solve 5 minus 2x, which is the input. I highlighted it, and you set that to be strictly greater than 0. That's all you have to do is solve its inequality. Good, so let me subtract 5 from both sides. So I'll get -2x is greater than -5. Now divide both sides by -2. Be careful when you do that. You do need to flip the inequality facing the other direction. So this will be x is less than 5 over 2. Actually, let me not box it. Okay, so flip, so going from here to here, flip inequality. So I hope everyone sees that. It's because I divided both sides by a negative number. Good. Now interval notation. So we're going less than 5/2. So we want to do a minus infinity to 5/2 and open parentheses. I mean, the round parentheses, not the round brackets. Okay. So that would be the answer here. Okay, so we'll do one more. Yeah, we'll do one more. And just, of course, stop me if there's any questions.
So the domain of a logarithm can also be negative infinity?
Yeah, so we just need to ensure and verify that the input is always positive. And the numbers in this interval will ensure that the input is positive. Because that's the inequality we solved. We found the numbers that make 5 minus 2x to be positive.
Nice.
So yes, in this case, yeah, so the domain came out to be negative numbers. Yeah. Any other questions? All right, we'll do another example. Okay, log of x minus 5 plus 2. Okay, so what's different about this example? We have this plus 2. Anywhere in the steps, does it say to care about any transformations? Does it tell? No, it doesn't matter. So thus, the vertical shift doesn't change anything. So I just want to note that. The vertical shift up 2, which is the plus 2 on the outside of the log, doesn't change a thing, okay? You just care about the input of the logarithm. Doesn't change anything. All right, so you just have to solve the inequality. The input is x minus 5, and we set that to be strictly greater than 0. Okay, add 5 to both sides. You get x is greater than 5. And then, of course, our interval notation, we're going from 5 to infinity. Okay, so all you need to do is just set the input to be greater than 0. All right, so any questions? Okay. So on the portion of the homework that does these types of questions, I have an optional one. It's like part C of these types of questions. I'm just noting that, okay, so there's an optional one for like some extra credit. Okay. All right.
Is it possible to have like a union of both of them, but with some limits to it?
Yes.
Like so for instance, I'll just pick one. So x is greater than -4 or x is greater than -7. Like, is it possible to have both of them together, or would you have to like restrict one?
No, that is totally possible. So what you just said, that will happen when perhaps the input of the logarithm is like a quadratic equation. So in that case, you would be setting the quadratic to be strictly greater than 0. We didn't go over how to solve quadratic inequalities. That's why it's optional on that.
Okay.
But yes, you can absolutely get a union of intervals. Yeah, good. Any other questions?
Just stupid, but like the range never changes, right? Or
No, yeah, range, you're always going to get the whole entire real line.
thank you.
Good. Okay. All right, so let's move on to graphing. All right, we're getting close. Yeah. All right, we're almost done. All right, so let's get to graphing. Okay, so graphing logarithmic function. Okay. All right, I think I'm going to type just because there's a little bit to write here. So, okay, so we will, still red. All right, forget it. All right, we will show next class that log base b of x and b to the x are inverse functions to one another. Okay, we're going to show that next class. That in fact the exponential and of b to the x and log base b of x, they're inverses to one another. Okay, so that's a really nice property. So what's the consequence of this? Well, it has to do with the function tables. Okay, so thus, given a function table for b to the x, we can get the function table for log b to the x just by swapping the x and y coordinates. So I hope some of you watched those 3 inverse function videos that I posted on Moodle. So basically, to get the inverse of a function given in a function table, you just need to swap the rows. Okay, you swap the x and y coordinates, and that's your table for the inverse. Okay, we'll do that right now. Okay, so in fact, let's do this for the definitive case y equals 2 to the x. Okay, so thus this will give us the function table for log base 2 of x. Okay, so we're gonna make a function table for 2 to the x first. Then we will swap the x and y coordinates, giving us the inverse function table, and that will be the function table for log base 2. All right, so this is one way to get at the graph of a logarithm. Okay, so let's start with the function table for 2 to the x. So we'll have our x column, and then we'll have our f of x equals 2 to the x. Okay, so so the x values that are usually good to do, you just go from -3 to 3 and the whole numbers in between. So you could do -3, -2, 0, 1, 2, 3. So I'm going to plug in -3 into the function 2 to the x. That'll give me 1 over 8. Plug in -2, you get 1 over 4. Plug in 0, you get 1. Oh, I forgot -1. Oh, damn it. I forgot -1. Let's see if I can just split this up into 2. There we go. All right, plug in -1, you will get 1 over 2. So the first 3 entries, that's by our work on negative exponents. Okay. All right, now plug in 0. 2 to the 0 is 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. Okay, good. So this is just a good old-fashioned function table for 2 to the x. Okay, now interchange the x and y coordinates, and you have yourself a function table for log base 2 of x. Okay, for the function y equals log base 2 of x. Okay, why is there a subscript 2? Why is the base of the logarithm 2? That's because we are getting it from the function 2 to the x, where 2 is the base. That's the connection. Okay. All right, there we go. So let's do it. So we have x, and then we have y is equal to log base 2 of x. Okay, so all I'm going to do, I'm just going to swap the rows. So it will be, instead of -3 1/8, it's going to be 1/8 -3. So it'll be 1/8 -3. Okay, instead of -2 1/4, it's going to be 1/4 -2. And so on. Okay, so I'm just going to repeat this game for the rest of the table. Okay, I'm just swapping the rows. Okay, good. So 1/2 -1, 1 0, 2 1, 4 2, 8 3. Okay. So any questions on how I obtained the function table and why it's a function table for log base 2? Okay, so it is a function table for log base 2 because log base 2 is actually the inverse function to 2 to the x, which we're going to show next class. All right, we're just going to kind of take that on faith right now. Okay. Okay, good. So I have a picture of this graph. That's what I'll show you now. Right. Awesome. Okay, good. So actually, I have the graphs of both functions. I have the 2 to the x graph. That's the blue guy. And then I have this orange graph. That's the log base 2 of x graph. Okay. And you may be asking yourself, oh, why is there a dotted line of y equals x? Well, graphically, to get the graph of an inverse function, you need to reflect over the line y equals x. That's how you get the graph of a function's inverse. You reflect the graph of the function over the line y equals x, and that will give you the graph of the inverse function. All right, so that's why that's there. And you can kind of see if you flip it over the y equals x line, you get exactly log base 2.
Does y equal x refer to like that it has the same slope as x?
No, so it refers to that you're interchanging the x and y coordinates.
Okay.
So a coordinate here, how can I write on this? Yeah, so you see how there's a coordinate 1, 2 on the exponential? That, when you reflect over y equals x, that coordinate gets to 2, 1 right here. You interchange the coordinate pair.
I see.
So that's the graph. That's the graphical interpretation of reflecting over y equals x. You interchange the coordinate pair. So
Got
1, 2, 1 to 2, 1, and that's actually that's what we did on the function table here. 1, 2, 1 to 2, 1.
Got it.
All right, awesome. So that's what it looks like. So the orange, by the way, just to reiterate, that's the logarithm graph. Okay. All right. So where are we at now? Okay. All right, so I'm at that point where I'm just going to rattle off a bunch of properties of the graph, all right, like asymptotes, domain, range, x-intercept, and so on. So let's just get that. Okay, so properties.
Do logarithms have y-intercepts or no?
Y-intercepts. They can if there were a horizontal shift. You see, if I shifted the orange to the left, it would hit the y-axis.
Yes.
Did you say y-intercept or x-intercept?
Y-intercept.
Oh, y-intercept. Yeah. So we're gonna get to that. We're gonna do that right now. All right. So I'm just gonna list just like a bunch of properties of the function and its graph. Okay. All right. So just as usual, you just to set up the notation, let b be strictly greater than 0, but it's not 1. Okay, and we're going to let f of x be log base b of x. Okay, that's, all right, so here we go. Here are the properties. All right, first, it is 1 to 1, so that's nice. And you can see that it's 1 to 1 by inspecting the graph of log base 2. And you can see that it passes the horizontal line test. Okay. Okay, but it turns out all of the logarithms will be 1 to 1, no matter what the base is, as long as it's greater than 0 but not equal to 1. Okay, so 1 to 1, which is great. We do have a vertical asymptote at x equals 0. So we have a vertical asymptote at the vertical line x equals 0. And you can see that. We see that the graph down here, it's getting arbitrarily close to the x equals 0 line, but it's not touching it. But we do have this behavior down here of an asymptote. Good. Okay, and I'm just going to reiterate the domain and range again, just for the sake of completeness. So again, domain is 0 to infinity. Range is the whole real line, so you're going to get minus infinity to infinity. Good. X-intercept. At 1, 0. Okay, 1, 0. Also, so it's always going to have the point 1, 0 on its graph, and there's another key point. It will also have, so we'll always have the point b, 1 on its graph. Okay. So let's think about why these two things are true for a second. Why will it always have 1, 0, and why will it always have b1? Okay, let's look at the first one, 1 comma 0. So that means that log base b of 1 is 0. Is this true? That's what the coordinate means. If 1, 0 is on the graph, that means that this equation is satisfied. Well, go to exponential form. This is b to the 0 equals 1, which is true. That's why 1 comma 0 is on the graph. Okay, next, how about b comma 1? Log base b, see the b is the input, equals 1. Is this true? Well, go to exponential form. Rewrite it as b to the 1 equals b, and that also true. So that's just a proof that 1 comma 0 and b comma 1 will always be on the graph of log base b of x. Right. All right, so I'm just going to erase this just so because it just looks a little out of place, but yeah. Okay, good. And one more. So we have the increasing and decreasing behavior depending on what the base is. So b greater than 1, that will be increasing. And what else? Right, b is between 0 and 1. This will be a decreasing graph. Okay.
But will it ever cross the y-axis? I
The
mean,
y-axis, not without a transformation.
oh, okay, so only with a transformation, then it can have a y-intercept or
Yeah.
crossing.
Exactly. With the transformation, you can get a y-intercept. Because look, if, as I said, if you horizontally shift this to the left, you will hit the y-axis here. So you will get a y-intercept.
Got it.
But the parent function, log base b of x, no, there's no y-intercept. We have this vertical asymptote at x equals 0.
Got it.
Okay, yeah, so I just have a picture of the increasing, decreasing behavior. Yeah, good, okay. Yeah, so this just highlights, look, if b is greater than 1, that's this left graph. Look, it's increasing. As I travel on the x-axis, the y values are getting bigger. It's a direct correlation. X goes up, y goes up. That's increasing. But when the base is between 0 and 1, we have an indirect correlation. X values go up, y values go down. Indirect. Okay, X goes up, y goes down. All right. Okay, so let's do an example. Let's start graphing these guys, okay? Okay. All right. So the question will be graph y equals log base 5 of x. Okay, and the way to do this is, I think the easiest thing is to get those 2 points on the graph and get the vertical asymptote, and then it's a very easy thing to do. So first of all, we know the points 1 comma 0 and 5 comma 1 are on this graph, okay? We know that by our discussion earlier, scroll up to this guy, we will always have the point 1, 0 and B1 on the graph. B here is 5, so we have 5, 1 on the graph. Good, and also we have a vertical asymptote at x equals 0 That's another piece of data. And our B value is 5, which is greater than 1. So it's increasing. Okay, and with this information, you can graph it pretty easily. So let's just see what that looks like. So I'm going to draw my XY axis. Okay, so let me plot the point 1, 0, and 5, 1. So let me 1, 2, 3, 4, 5. 1, 2. Okay, so let me go to 1, 0. That's the point right here. And 5, 1, 1, 2, 3, 4, 5, 5, 1. Okay, and we have a vertical asymptote at x equals 0. So we have this dotted line going here. Okay, so this is what you do. You kind of just start down at the vertical asymptote, cross these 2 points, and that's really it. So it just looks something like that. So all you need, 2 points on the graph and the asymptote, and it's follows this shape. That's really it. Okay, so any questions on anything? This is really all I would expect for a sketch of a graph. Yeah. Okay, very good. So I think this, right. Good. So the last thing we will do are transformations of the logarithm. Okay, that'll be the last thing we'll do tonight. So this will be transformations of logarithmic functions. What does that mean? What are transformations? Yeah, those are just our vertical shifts, vertical stretches, and horizontal shifts, horizontal compressions. All right. So let's just talk about that in the case of the logarithm. Okay. So here we go. So in general, a transformation So in general, a transformation of, a transformation of f of x equals log, f of x equals log base b of x will looks like what? Well, this should look sort of familiar. We'll have a times log base b of x plus c, and then plus d on the outside.
In that log b, and then you have parentheses, does that like multiply the base or no? It doesn't mean that.
No. The subscript b is just telling you what base the logarithm is. It's just a piece of information. Oh, well, this is log base b. X plus c is the input. That's what you're inputting into the function.
Got it.
Yeah. No, so it's not multiplication. It's a subscript. All right, good. And let me just tell you what these letters are, but I think you guys know what these letters are. So A is going to be our vertical stretch. So sorry, I'm not really writing too well today. So A is the vertical stretch. Good. That C is a horizontal shift. Okay, nothing new here. And the D will be a vertical shift.
You wrote X is horizontal shift. Do you mean C is?
Oh, yes. Thank you. Yes. Yes, C is horizontal shift. Good. So you may be asking, oh, where's the horizontal compression, horizontal stretch? Again, just like in the case of the logarithms, just as in the case of the exponentials, we do not need to consider horizontal stretches or compressions, which is very nice. That will become clear next class when we do properties of logarithms. Okay, so I will explain why next class we don't need to worry about horizontal compressions or stretches. But for now, just take my word for it. We don't need to consider them. And that will follow by some properties of the logarithmic function.
Do we need to consider a vertical compression, or is it just a vertical stretch?
Oh yes, vertical stretch / compression, definitely. So a stretch will be when A is greater than 1, and a compression will be when A is less than 1.
The reflection also counts for both of them, for Y and X.
Yeah, so a vertical stretch, yes, a reflection about the y-axis will be when A is negative.
And it can go about the same order, whether you do a stretch first or if it still fits into that, about the y-axis.
Yes, you can vertically stretch, then reflect over the y-axis, x-axis, or the other way around.
Yeah.
Good. Okay, now we have this transformation, okay? Let me tell you properties of this guy so we can graph transformations really easy, just really easily. Okay, so first of all, what is its domain? So the domain of this guy will be, okay, does someone want to tell me what the domain of this transformed logarithm is? It should follow from our work from earlier. What do I need to do here?
Isn't it the same negative infinity and positive infinity? You're not
that was the range of the logarithm.
Oh, okay.
For a domain, we needed to ensure that the input was strictly greater than 0. So what should I do?
So C to infinity?
Close. Minus C to infinity.
Minus.
Because you need,
because plus C.
Yeah, you need to, it's going to be all x values that satisfy x plus C is strictly greater than 0, and that will be the same as x is greater than negative C, and then in interval notation, that's minus C to infinity. Okay, so...
The rest of the transformations don't matter for the domain, right?
No, they don't matter at all, yeah. Base, stretch, vertical shift, they play no role in finding the domain. So the domain will be, I'm just going to write it again, it's going to be minus C to infinity, and just here is just like the work on how I got that, okay? Good. Okay, now, how about the vertical asymptote? Okay, so a vertical asymptote will always occur where the log input can become 0. Okay, it's going to occur when the logarithmic input is 0. So that will happen precisely when the input x plus c is 0. And this is, you solve this equation, it's going to be at x equals negative c. Okay? So vertical asymptote at x equals negative c. How did I get negative c? I set the input to be equal to 0 and solved. Okay? Good. All right, and here is what I think is the most interesting. So do you remember up here when we did properties of the graph, we had the 2 points 1, 0 and b, 1. What are those two corresponding points on the transformation. And this just looks really cool and actually comes out kind of nice. So this passes through the points. Okay, so the 2 points, you are 1 minus c comma d, 1 minus c comma d. Okay, that's one xy pair, and the second one, b minus c is your x coordinate, comma a plus d. Okay, so how on earth did I get these x and y coordinates? What I did is I took the point 1, 0 that's on the parent graph, it's on the toolkit graph, and I applied the transformations, the vertical stretch, horizontal shift, and the vertical shift to 1, 0, and I got 1 minus c comma d. And then I applied the same transformations to the point b comma 1, and I got b minus c comma a plus d. Okay, that's where these 2 points came from. So you remember those questions on the homework where I was like, where does the point 7, 7 get sent to under the transformation blah, blah, blah? I did just that sort of thing to the points 1, 0 and b comma 1. Okay, so this I thought came out to be a very interesting expression. I thought that was kind of cool. All right, so let me just write what I just said, and if you want me to do it, I can. Yeah, so let me know. So these points are obtained by applying the transformation to the points. Transformation to the points 1, 0 and b comma 1 respectively. Okay, so I'm just explaining how I got these points. I'm not pulling them out of thin air. There is a method to how I got them. I applied transformations to 1, 0, and I got this guy. I applied the transformations to b comma 1, and I got this guy. But the transformation I applied was a general one in terms of a, c, and d. And that's why the points are expressions of a, c, and d. Okay. So we're going to do a concrete example of this, and it will come to life. All right, so any questions? All right, so we just have one example, and then we will be finished, okay? So, example. Okay, so state the vertical asymptote and 2 points on the graph of f of x equals 2 log base 5 of x plus 4 plus 5, and then sketch its graph. All right, let's just do this one thing at a time. Let's go really slowly. So vertical asymptote first. Okay, so I'm just going to shorten that to VA. Okay, so the vertical asymptote happens. Okay, the vertical asymptote happens when the input of the logarithm is 0. So you set x plus 4 to be equal to 0. Solve that guy. That will give you the vertical asymptote. So it happens when x plus 4 is 0, which is x equals negative 4. Okay. So it happens when x plus 4 is 0, and that's precisely when x is negative 4. Okay, good. Now, to get the 2 points on the graph, we need to identify our vertical shift, vertical stretch, horizontal shift, vertical shift. So let's do that. So here, A, which is the vertical stretch, what is that? That's 2. It's that coefficient in front of log. Okay, so here A equals 2. The base of our logarithm is 5, so B is 5. C, which is our horizontal shift, that's the plus 4, so C is 4. And D, which is the vertical shift, that's 5. Okay? So I hope everyone can see where I got these A, B, C, and D numbers from. I just read them off from the function. Okay, and why do I need them? It's because I can get the 2 points that the graph passes through. So the graph passes through. Okay, the first one, remember, it was 1 minus C, comma D. 1 minus C, comma D. So that was up here when I listed the properties. It passes through the points 1 minus C, comma D. All right, so it's going to be 1 minus, C is 4, so I put a 4 here. So 1 minus 4, comma D. D is 5. All right, I just plugged in 1 minus C and D. And this simplifies, so the x coordinate is just negative 3. This is negative 3, comma 5. Good, so we just figured out 1 point on our graph. How cool is that? So negative 3, comma 5. And we have 2 points. The second point, so scroll up, another point on the graph is B minus C, comma A plus D. And B minus C, comma A plus D. Okay, so that's why I listed A, B, C, and D first, so they're easily, so we can call upon them very easily. Okay, so B minus C, I'll have 5 minus 4. Wait, hold on. Yes, okay, sorry about that. Yeah, so 5 minus 4, B minus C. And the second coordinate is A plus D. Well, A here is 2 and D is 5, so it's going to be 2 plus 5. And now just do the addition. Here you'll get 1, comma 7. And that's another point on our graph. Very good. So now we just take all of our data and we just put it on a graph. Okay, so firstly, I like to put the vertical asymptote on with a dotted vertical line. So at x equals negative 4, I'm just going to put a dotted line. So negative 1, negative 2, negative 3, negative 4. So that's the asymptote at x equals minus 4. Next, I just like to plot my points, negative 3, 5, and 1, comma 7. So 1, 2, 3, 4, 5, 6, 7. Okay, first I'll do negative 3 comma 5. So negative 1, negative 2, negative 3. 1, 2, 3, 4, 5, something like that. So that's negative 3 comma 5. And then I'll do then I'll do 1 comma 7. Yeah, 1 comma 7. So that's over here. And that's 1, 2, 3, 4, 5. So that's right over here. So that's 1 comma 7. Okay, so this graph is not going to look the best, but I think you guys get the idea of the procedure. Now, go down to your vertical asymptote and connect those 2 points. Something like that.